Okay, so I think we can start. Hi, everyone. Welcome to another Human-Centered AI seminar, this time online. We're very happy to host Elizabeth Bondi-Kelly. Let me know if I mispronounced anything. So Elizabeth is currently a postdoc at MIT and an incoming assistant professor of electrical engineering and computer science at the University of Michigan. She's completed her PhD in computer science at Harvard with the Professor Milind Tambey's group. And her research interests include multi-agent systems, remote sensing, computer vision, and machine learning. And most particularly, which is really interesting for us, is that she's applied these to conservation and public health and social good issues, which is again something that Monash is very keen on promoting. So today's talk is going to be about challenges in building and deploying multi-agent systems for social impact. And she's going to be talking a little bit about some of the work that she has been doing in her PhD and some of the work that she's going to be pursuing now. That's it. So let's welcome her, and I'm sure it'll be a very interesting talk.
Thank you so much. Thank you very much for the kind introduction and the invitation to be here with you all today. I'm really sorry I'm not there in person, but I'm glad to be able to join you remotely today. So with that, I'm happy to get started and share some of this work on AI for social impact. So just to get started, I believe that artificial intelligence, or AI, has lots of promise to improve lives around the world, especially through use-inspired research in public health and conservation. And I've sought to do this so far through partnerships with stakeholders in both domains. So first, in public health, I've studied micronutrient deficiency in Madagascar in collaboration with public health researchers and Mahiri, a public health and environmental research organization operating in Madagascar since 2004. And second, in conservation, I've worked to prevent illegal wildlife poaching using conservation drones in collaboration with an NGO called Air Shepherd. And I've also created a nonprofit called Try AI, which is devoted to increasing diversity and inclusion in AI and exploring AI in society broadly as well. So in my experience, work in these domains can be broken up into a pipeline that I think is widely applicable in AI for social impact. I've typically started by gathering and analyzing real-world data, then using multi-agent reasoning for recommendations, like resource allocation, for example, and finally deploying, which might lead to more data collection and analysis later on. But several challenges arise because it is AI for social impact. First and foremost, we may have limited noisy data, which can amplify uncertainty. So in this real-world image from the conservation domain, for example, I think it's pretty difficult to tell exactly what it shows. It happens to contain lions, which we'll discuss a bit more later. But with this uncertainty present already at the first part of our pipeline, what will happen later on in the pipeline? And we also need to plan on interacting with humans in most cases. For example, during deployment, when we give someone our system to use, they might also provide or label data and have values or behaviors we should account for during planning. So really, we likely have humans involved at each stage as well. So in my work, I seek to address these challenges throughout the AI for social impact pipeline. And a few highlights from my work so far are my algorithms to account for uncertainty in security games with signaling, bandits and data augmentation strategies to handle limited data, field deployment of an algorithm for conservation drones, and demonstrating the impact of model predictions and uncertainty on human decision-making. So I'll go through these in more detail through these 4 sections. In the first section, I'll emphasize the systems I've developed for handling uncertainty, and I'll describe this in the most detail. Then I'll briefly show that we can work with humans and use data augmentation to address uncertainty. and that we need to have interdisciplinary inclusive teams during development and deployment. And I'll conclude with summarizing a few key takeaways and discussion. So throughout these sections, I'll include both of those domains I mentioned, conservation and public health, and my nonprofit Tri-Eye at the end. So starting with section 1, and in particular, a more thorough introduction to this first setting. So we're going to start by thinking about the conservation domain, and specifically when we're trying to protect animals from illegal wildlife poaching. In other words, a defender is trying to protect targets from adversaries. In the past, Stackelberg security games have been used extensively to best allocate potentially limited defender resources in these kinds of scenarios, including in public safety, such as planning Coast Guard and Air Marshal patrols. For conservation, animals in the park are going to be located at targets in the park, and the defenders, or park rangers, are represented by light purple and the letter R for ranger, and the adversaries, or poacher suspects, are represented as light yellow with the letter A for adversary. And the goal of this Stackelberg security game model is to allocate the defender resources. So how do we determine where the defender should go exactly? In a Stackelberg security game, the adversary is allowed to observe the defender's strategy before choosing their own strategy. So if we say the defender commits to a pure strategy in which they protect animals at target 1 in the park, then the adversary can attack animals at target 2 to get a utility of 1 and leaving the defender with the utility of -1. Now let's say the defender commits to protect target 2 and the adversary chooses target 1 to get a utility of 5, but leaving the defender with a utility of -5. Instead of choosing one target at a time, we would like the defender to randomize probabilities over the targets, which is called a mixed strategy. And on a particular day in which we need to protect the park, we sample a pure strategy, for example, one of these targets, from the mixed strategy. It's still not 100% secure, but it increases the uncertainty and cost for adversaries. However, most prior work in Stackelberg security games was stationary and static. Park rangers wouldn't get to move around to multiple targets, for example. I started working with conservation drones in collaboration with Air Shepherd, which opened the door to noisy real-time information in these Stackelberg security games. So in this scenario with conservation drones, they fly around the park, often at night when poaching typically occurs, and provide real-time updates to park rangers. For example, by sending thermal images, which show heat, allowing us to see humans and animals like these lions. Rangers can monitor these from their base station and can alert nearby park rangers to investigate further. And hopefully, this could prevent poaching in real time, meaning we could save animals as a result. From my discussions with those flying conservation drones in the field, I also learned that park rangers could turn the lights on aboard the drone to alert adversaries that rangers are on their way in hopes that they'll run away before poaching. This is called a signal, and hopefully it's another strategy to prevent poaching in real time, again meaning we could hopefully save animals. While this real-time data could be really useful to preventing poaching in real time, limited resources and manually monitoring videos are two challenges to using conservation drones. I first worked to address this challenge of manually monitoring videos with automatic detection of humans and animals, which we'll discuss in more detail later on. First, we'll start with the challenge of best using limited resources. This is very important as some parks can be as large as US states like Massachusetts, for example, and it would be impossible to cover the entire area. So using a signal can help cover more area by creating an informational advantage. So I have a hopefully fun example of an informational advantage in a Star Wars movie for us to look at together. Here we have Han Solo in the front, facing off with some adversaries across the field there. So let's go ahead and see what they do.
You happen to notice that freighter down there? You know what's on it? About 30 hired guns. All I gotta do is give them the signal, you're surrounded.
Okay, so in this clip, Han Solo claims to have backup on the Millennium Falcon. The adversary hears this and is uncertain whether he's telling the truth, so has to make a guess about whether to attack or not. So Han Solo's informational advantage is therefore knowing whether or not they truly have backup on the Millennium Falcon. Hopefully, the adversary will not attack due to this uncertainty.
You happen to know.
So for the conservation scenario, we achieve this informational advantage through strategic signaling. So there has been some prior work that has considered strategic signaling in a similar real-time context. In particular, my lab mate Haifeng Xu and colleagues got the idea to investigate strategic signaling from the collaboration that I led with Air Shepherd. In their work, there's a signaling scheme to follow depending on whether there's a park ranger nearby. So in this example signaling scheme here, the drone will signal whenever the ranger is coming. But when there is no ranger nearby, which happens with 0.7 probability, the drone will signal with 0.3 probability. The rest of the time, the drone will truthfully not signal. So this means that it's a 50-50 chance for the adversary that someone is coming or not, making it better to run away when there is a signal, and it's now more frequently protected than not. So this takes advantage of an informational advantage in that the adversary doesn't know for sure whether there's a ranger responding or not, and leads the adversary to run away instead of poach. However, this prior work assumes perfect detection and only enacts this scheme if there is a detection. But what happens if there's a false negative detection? That is, humans are really there, but they aren't detected. I found this pretty commonly in my work on object detection. And another question could be, what if the adversary may sometimes not see the signal? It's not clear now if we can still have this informational advantage or whether signaling is still useful for preventing poaching at all. So I worked on a model to try to address this uncertainty, which I'll go through now. And let's start with having K park rangers and L drones, who can be allocated to different targets throughout a protected area. The targets are represented by a graph, where edges represent the ability of park rangers to respond within some fixed time. In my model, the defender commits to the plan or mixed strategy offline. Then each night, the defender uses this plan to select a pure strategy allocation. This is all present in the original Stackelberg security game model as we discussed in the earlier example. But uncertainty led me to introduce the additional signaling and reaction stages, which I'll describe in more detail shortly. But first, the defender utilities as this game plays out are positive if the park ranger successfully prevents poaching, but negative if an animal is poached. This is similar again to the example we went through earlier, but here we have to add a utility if the adversary runs away due to signaling. And we experimented with multiple values for this, varying between 0 and positive. So during the signaling stage, as we've discussed, our goal is to convince the poacher suspect to run away instead of poach. But what can we do about these false negatives? So first, I propose to signal even if there is no detection. This way, there's a chance that a signal still turns on even when we didn't detect a human, which helps bring back our informational advantage, because now the adversary isn't sure if we've detected them or if a park ranger is coming. And second, I propose to add the reaction stage. In this case, we may want to send a nearby patroller to double check. For example, if we know we have a poor detector, that is a high probability of false negatives. If we know we have a good detector, that is a low probability of false negatives, then we may double check elsewhere where there was no ranger or drone initially. And we called this movement in the reaction stage a matching. So now getting into the algorithm for this model called GARTS. To start introducing some notation, let's start by looking at a simplified setting where we just have rangers, specifically say we have one ranger, and in this pure strategy, we'll place them here in this center target. So we're going to encode this pure strategy using a vector E. The probability of this pure strategy in the mixed strategy is represented by Q sub E. Note that there is a set of feasible E and corresponding Q sub E. For example, there's a probability of allocating the ranger to another target. So our goal in Stackelberg security games is typically to find a mixed strategy that maximizes defender expected utility, subject to feasibility constraints and taking into account the adversary's best response. This can be encoded using a linear program or LP. And for anyone familiar with Stackelberg security games, I'm using the multiple LPs approach. So this is an LP for a single target. And once again, this one is simplified to not include drones at all. So first, maximizing defender expected utility is based on whether there is a ranger or not, and the defender utility if there is a ranger or not. So for feasibility, recall that the Q sub E is the probability playing pure strategy E. So in brief, X is a marginal probability of a target having a ranger based on these pure strategies. And we only look at pure strategies that have a ranger at that target. And finally, we take into account the adversary's best response. However, my pure strategy space for signaling under uncertainty is more complex because I need to handle signaling and reaction. We no longer just have a ranger present or not. Now we also have a drone present or not, plus the ranger's movement in the reaction stage. So this makes the problem more complex with more constraints and pure strategies. For example, the total number of E is now 6 to the n instead of 2 to the n. So we have to make a few changes to the LP to account for these additions. I have to update our utilities to incorporate drones, and I need to add signaling probabilities for detection and no detection. But this gives us the full LP. To solve this more complex model, I adapted the branch and price approach. For anyone who knows that branch and price has both branch and bound and column generation steps, in the interest of time, I'll only focus on my novel implementation of the branch and price approach, particularly in the column generation component. So column generation helps us handle this challenge of having an exponential number of pure strategies. For anyone who may not be familiar with column generation, it's a way to start solving with just a few pure strategies and slowly add more. We can decide which strategies to add using a secondary problem. And here, I designed the secondary problem using a directed graph to account for the reaction stage. So for example, if I added constraints to ensure a directed edge is included if a ranger is matched to a neighboring target. So now we can continue to add pure strategies based on the result of the secondary problem until the pure strategies no longer add to the optimal objective value. So now let's see how this algorithm performs. First of all, with some timing results. So here the x-axis has the number of targets and the y-axis has runtime with a time limit of 1 hour. So while the problem is still NP hard, my proposed guards algorithm scales a bit better than the original exponential LP and can include up to about 100 targets when running for 1 hour. But now, the more exciting part, to show why uncertainty is so important. So here on the x-axis, detection uncertainty is increasing to the right, and the y-axis has defender expected utility, where higher is better. So in this first plot, we see the results from guards, the algorithm that I proposed, when we have different numbers of resources. The performance decreases as uncertainty increases along the x-axis. We also see a large drop in performance when we ignore detection uncertainty during planning. The magnitude of the decrease of defender expected utility for guards in the right plot is similar to the left, just with different scales due to the really large decrease when we ignore uncertainty. We also showed both observations theoretically. First, we see that higher uncertainty leads to lower or similar defender expected utility. And second, that defender expected utility when we solve assuming there's no uncertainty is less than the defender expected utility when we solve with the true uncertainty. So in other words, ignoring detection uncertainty will lead to worse performance. I think this highlights the importance of accounting for uncertainty from the first stage of the pipeline while doing multi-agent reasoning. So moving on to discuss another approach to this problem. Together with lead author Arvind Venugopal, we also approached it with reinforcement learning as another way to simulate possibilities and try to figure out the best action to take. So similarly to guards, we consider allocation and an additional stage for signaling and moving again, which we call patrolling. This time, there are additional movement possibilities. The interesting part of this algorithm is that it is also decomposed. We train the patrolling first based on random allocations to get a patrolling policy that includes movement and signaling. And this relies on a multi-agent reinforcement learning algorithm that could be used interchangeably. Then we train the allocation phase to get an allocation policy. And training is done by sampling an allocation and getting the reward from running the patrolling stage. In terms of results from this strategy, defender utility is once again on the y-axis, and higher is better, and uncertainty is increasing along the x-axis. So our reinforcement learning approach performs better than the baseline opt-grad FP as uncertainty increases. Like guards, we can also see a decrease in performance as uncertainty increases. So once again, uncertainty is important. So now let's consider the scenario where we've been strategically signaling for a really long time. For example, let's say that every time the adversary arrives at a target, there happens to be a signal. We are planning this strategically, but perhaps the adversary is not playing rationally and starts to take it into account less as they see the signal more. This is an example of bounded rationality. So together with lead author Sarah Cooney, we further investigated this effect of signaling frequency on boundedly rational humans. And in particular, we looked to modulate the frequency with which we're signaling to account for this effect of desensitization to signals. In short, this means that we need to modify our LP that we just discussed to try to also find a signaling frequency F. However, we also have to account for the probability of the adversary attacking when signaled with frequency F, which we'll call alpha. And this is unknown currently. So to determine this probability alpha, we studied human behavior in human subject experiments on Amazon Mechanical Turk. In particular, we varied the adversary rewards, the coverage probability, and the frequency, and provided the instances for humans to interact with. While we believe our findings generally apply in the conservation domain, we designed this signal for a cybersecurity setting. For example, if you are an employee trying to access inside information. We then trained a neural network to learn the probability alpha based on over 17,000 instances of signaling. So now we can solve for the signaling scheme with a modulated frequency and test this new model in further human subject experiments. So in terms of results, we again have defender utility on the y-axis, again, where more positive is better. And along the x-axis here, we have the multiple rounds during which humans interacted with this system. So compared to the original baseline we discussed, Shu et al. 2018, our method accounting for bounded rationality is achieving better performance across all rounds. So to summarize so far, we've discussed accounting for uncertainty based on the initial data gathering stage during multi-agent reasoning. And now, in the next section, we'll look further into human involvement in these systems. Specifically starting with selective prediction. So in order to initiate responses like signaling or rangers checking on targets, recall that we may need to communicate with park rangers once we've detected a human or animal. One way this communication can work is through selective prediction. In selective prediction, when we have an image, an AI model will try to predict its contents. When there's uncertainty, we can ask a human what the contents are, which we call deferring to a human. And this can often increase performance over either the AI model or the human individually. But most prior work on selective prediction assumes that if an AI differs, a human would just label it as though they aren't influenced by the interaction. So therefore, they use synthetic data sets or pull old human labels from when they observed the image initially. However, recent work has shown some impacts on human behavior when they interact with model predictions, for example. So we wanted to know what happens in a scenario where we truly have a human in the loop in this selective prediction setting. Are humans impacted by the way we present such a decision to them? I led a human subject experiment to try to answer these questions. So rather than use thermal images for this particular experiment, I used a similar conservation data source, specifically camera trap images. So these images are captured when they detect motion, which can help scientists observe animals. Sometimes, though, they're falsely triggered by motion caused by wind, for example. So it becomes important to determine if there are animals present in the images. In fact, a question for the audience here: do you see an animal in this particular camera trap image? Feel free to shout out your thoughts. Oh, I see something in the chat. Yes. Awesome, thank you for participating. Yeah, the answer is yes, indeed. And similar to asking all of you now, I trained an AI model to try to answer the same question. And on images for which the AI model was uncertain, I collected them to defer to our human participants. So that way they can make the final decision of whether an animal is present or not. So participants were first trained briefly. We told them about camera traps and went through some examples with explanations, including the one that we just did together. Then we mentioned adding the AI model as shown here. This is followed by a few examples with the AI model predictions, followed by explanations. I do want to note here that we mentioned that deferral means it is uncertain. So then, once we go to the deferred images, I varied the message showed to participants before they made the decision about animal presence. There were 4 types of messages: no message, deferral message, prediction message, or both. And the exact messages are shown on the top right. So for example, the deferral message simply says AI model deferred. The prediction message, on the other hand, gives the uncertain AI model prediction. So then the participants can see the image and they can decide whether there's an animal present or not. In this case, we can see from the circle around the animal here which is just for the presentation, but not for the participants, that the AI model's prediction of no animal present is incorrect. So I invited 198 participants on a crowdsourcing platform called Prolific, which is similar to Amazon Mechanical Turk. I had 80 of these deferred images, which are balanced in terms of whether the uncertain AI prediction was correct or not, and whether they contained an animal or not. There weren't any repeated images. I never told users that all were deferred, and each image was randomly allocated to one of the 4 message types. I did this random allocation 4 times and sent 50 participants to each version. Once the experiment was complete, I ended up finding statistically significant differences in accuracy between the 4 message types. And in particular, for this data set and for these participants, we saw an improvement in accuracy for defer only compared to no messages. And we think this is because it may serve as a cue to concentrate harder. But we also saw that predict only is performing worse than no messages. And we were curious to find out more about why this happened. So to better understand this decrease, when we show a prediction, we calculated conformity, which we defined as how much humans increase their agreement with the model when the prediction is present. So we found that humans do use the model prediction since the conformity is greater than 0, especially when they have low confidence, where the conformity is higher. So we can see that humans use the model predictions, but why is it a decrease rather than an increase? So as shown by the decrease in predict only incorrect compared to no message incorrect, that's these 2 orange bars that I highlighted here, we found that exposing humans to incorrect predictions of the AI model makes them even more likely to be incorrect. And furthermore, on the plot on the right, we analyzed the participant accuracy when there were no prediction messages. So participants are correct 66% of the time when the model correctly predicts animal or no animal, but only 50% of the time when the model predicts incorrectly. So participants and the model tend to err on similar images. So because of this, we should try to carefully present the AI model uncertainty and prediction to humans during deferral, for example, by only telling them that the AI model deferred. If we do this, then humans can help us overcome the AI model uncertainty. And before jumping into this next paper, I'll just mention that now during my MIT postdoc, I'm starting to investigate a few other questions here. So I'm happy to talk more about that towards the end. But there are a few open questions, like what happens when we have people of varying levels of expertise participating in these deferral systems or using AI models in general, and a few other questions that I think are raised by this study. So happy to discuss more later. But first, I'd love to tell you about another way that we can collaborate with humans to address uncertainty. So now let's think about a similar conservation domain where we are once again trying to prevent poaching. But instead of a real-time intervention with the conservation drones, the goal here will be to remove traps that have been placed by poachers. So furthermore, let's say that this is a brand new park and we don't have a lot of data about where the traps are being placed yet. So despite the uncertainty about where traps are being placed, we still need to prevent poaching by collecting traps in hopes of protecting animals. In this case, we want to visit underexplored areas to improve our model of where poaching may occur, which is an example of exploration, while also still removing traps in areas that we know to be high risk for poaching, which is an example of exploitation. So balancing exploration and exploitation is a setting in which the multi-armed bandit model excels. And applied to this setting, a multi-armed bandit means that we're deciding whether to keep patrolling one target or try a neighboring target, which may allow us to collect more traps and save animals. So together with lead author Lily Hsu, we created the lizard algorithm based on multi-armed bandits to determine a patrolling strategy that balances these goals of collecting data and finding traps. So the input to this algorithm is N targets with features associated with them. And the goal is to determine how much time a patroller should spend in each target to find as many traps as possible. So the arms in this multi-armed bandit are based on the targets and the amount of time at a target. And the reward is how many traps we find and remove. Because finding traps means saving animals, it's important to design an algorithm that will lead to finding as many traps as possible as quickly as possible. So the algorithm therefore exploits several characteristics of the problem domain to try to help achieve this goal. So for simplicity, let's suppose we have one feature associated with the targets, specifically elevation, which differs by 100 feet, let's say, for these two targets. So we need to estimate the reward at each of these targets. Let's say that we've explored target 1 multiple times, spending multiple amounts of time there, and consequently updating our understanding of the reward at that target. So the reward at target 2 would then differ by no more than the difference in elevation times Lipschitz constant. So using this domain characteristic allows us to estimate rewards at similar targets even if we haven't visited them yet. So do these domain characteristics help us? In these results, the x-axis has time steps, and each time step is 1 week. So by the time we get to time step 50, we've already been patrolling for 1 year. The y-axis is a percentage, where 100% represents the optimal patrol strategy, expected number of traps found. The optimal patrol strategy is computed by solving a mixed integer program based on the real-world reward functions and subject to a budget constraint. And 0% is naive exploit, which greedily selects the best action based on historical data. So yes, by taking advantage of some of these domain characteristics, Lizard can help us find more traps and more quickly, which means hopefully fewer animal lives lost to traps. So to summarize this section, we went through 2 examples of human-agent interaction and collaboration to try to address uncertainty. Now on to the next section on data augmentation to address uncertainty, starting with labeling. So we're now going to bring up the challenge of manually monitoring videos again with conservation drones. And specifically, our goal is to automatically detect humans and animals in these videos. So the first challenge towards detecting is that we have somewhat limited data compared to some other image data sets like ImageNet. While ImageNet has 14 million images, for example, we only have 62,000 thermal images from our drones. And additionally, I hope you'll agree that the lines look pretty different between the 2 data sets. So we likely can't just use ImageNet directly, unfortunately. So I developed a labeling tool to label these thermal videos called Viola, which was semi-automated. And I led a labeling team to generate 180,000 individual human and animal labels. This labeling process took about a year, so it was quite an investment to work with these real-world data. But it allowed me to train an object detector for humans and animals, which was our goal originally. I then worked towards deploying the object detection system in the field with our collaborators at Air Shepherd. I built this GUI in which they are alerted, optionally with a sound, upon detection, and they can optionally confirm a detection. We field tested this object detection system and found a 60-time improvement over Air Shepherd's original tool, which led to deployment. This deployment was the result of a multi-year collaboration with Air Shepherd, which involved many hours of discussions and screen sharing including while Air Shepherd was in the field whenever possible. And I found that to be a really important part for successfully deploying this for a little bit. But I also wanted to further improve performance and find a way to require less labeled data in the future. So to get more images without spending the enormous time and money required for collecting and labeling more, we turned to simulation. So here you can see a drone flying around a simulated African savanna, and eventually we come to see some elephants here. I used this simulated environment to estimate what a thermal image would look like based on identifying the objects for free because of the simulation and estimating their properties like typical body temperature. I generated 100,000 of these images and used them to improve our performance within a few hours rather than a few months. And specifically, I used domain adaptive faster RCNN, given the slight differences in simulated and real data. So these data proved important for developing and deploying the system in the field and took a great deal of time to curate, so I made them publicly available. Both real and synthetic data are available at this link and hosted by Microsoft if you're interested in exploring further. So this next approach to address uncertainty makes use of multimodal data. And to explore it, we'll focus on the public health domain that I mentioned at the very beginning. Specifically, micronutrient deficiency is a lack of vitamins and minerals, which impacts about 2 billion people worldwide and can unfortunately lead to severe physical and mental impairment. Interventions are possible, including supplementation, but they can be expensive. And unfortunately, to determine whether people in a population have micronutrient deficiency, blood draws are required. It's also possible to use surveys about what foods people have eaten to try to estimate micronutrient deficiency. So, Mahiri, Catholic Relief Services, and Harvard personnel collaborated to collect both data types in 2017 and 2018 in Madagascar across multiple regions. However, these are expensive and time-consuming to collect, so they were only collected over several regions, and they aren't collected very frequently. Satellite data, on the other hand, has been used in past work to predict agricultural health and socioeconomic status, for example. So here, I proposed to use satellite data for micronutrient deficiency prediction, despite not being able to directly observe it from a satellite. In short, this is because micronutrient deficiency may be influenced by many factors that are visible in satellite data, like agriculture, socioeconomic status, and forest cover. And they likely have to do with access to resources. So I therefore collected publicly available satellite data, which is thankfully less limited than our ground truth data. And I pre-processed these data such that they were normalized and aligned. Then I used feature selection to determine which of these types of satellite data to use, as with limited data, there could be a risk of overfitting with too many features. So to do feature selection, I first flattened these satellite features. And here I'm using 2 pixels for illustration. So we can plot these vectors according to their pixel values and then cluster them. In this case, we used the K-medoids clustering algorithm. I proposed to use correlation as the distance metric to remove highly correlated features while keeping one representative feature. This performs comparably to a public health expert choosing features to preserve and discard by hand. Okay, so now we have our features selected, and I then used logistic regression to predict micronutrient deficiency, which allowed for more interpretability for public health experts. To evaluate the performance, I compare this to the ground truth micronutrient deficiency biomarker data by aggregating micronutrient deficiency statuses across a region. This process of cleaning and aggregating the ground truth data collected by Mahiri and the team was another example of time-consuming but important real-world data collection and analysis. In fact, using satellite data led to improved performance compared to using surveys for prediction over all ecological regions studied for this micronutrient and according to the area under the curve metric. This shows promise for filling in the gap in places with limited ground truth data, which may hopefully support future interventions. So to summarize this section, we went through a few examples of addressing uncertainty during data gathering and deployment to inform future planning and deployment. It's now time to switch gears to the last section of the day on interdisciplinary inclusive teams. So far, I've discussed working with public health and conservation experts, and both collaborations have been vital, especially when considering deployment. But can something more be said for how to develop, deploy, and evaluate AI systems in general? Along with interdisciplinary co-authors from computer science and philosophy, we proposed a new framework to address these questions. And our goal was to define AI for good in a specific context in collaboration with the community most impacted by it. This goal is based on the capabilities approach, which prioritizes the ability of people to function as they wish. The UN was also inspired by the capabilities approach to create the Human Development Index, which is shown in the map here. But how do we understand the kinds of lives that individuals value? My team and I proposed to use a participatory approach to try to involve all stakeholders in the development and deployment of these systems. As part of this, we proposed a set of guiding questions to help implement the framework, and I've sampled 2 to briefly look at together. So one of the first questions we asked is, how are impacted communities identified? In my experience, nonprofits can be great places to start, as long as we can build a long-term relationship with them and others who could be impacted by the AI system we're developing. And second, I think it's important to determine what these stakeholders wish to achieve and measure capabilities when evaluating a system based on that. I hope that some of these questions and lessons learned can help guide researchers in developing and deploying AI systems for social impact in collaboration with communities, including for my future work. And another way that I've sought to increase inclusion in building AI systems is through TryAI, the nonprofit organization that I founded. Our goal here is to increase diversity and inclusion in the field of AI by supporting students in exploring AI in society. We're primarily working with high school and early undergraduate students, particularly those from historically underrepresented groups. Of course, there are many systemic barriers for those historically underrepresented in computing, unfortunately. But one in particular is the fact that potential real-world applications of computing and AI are not always discussed, especially when students are starting to make career decisions. But according to multiple studies, including one by McGee and Bentley, these applications can be really motivating for many in historically underrepresented groups in computing. It may also be difficult to tell what types of career paths are available without peers and mentors or opportunities to try them out. So to try to mitigate that, I've organized 6 events so far in hopes of supporting students in exploring computing and AI. We've done a micro-internship, a hackathon, and 4 speaker series with another micro-internship I'm planning for January. In a few more brief details, the micro-internship is a 2-week program where students work with mentors to propose an AI solution to a real-world problem of interest to them. So here we have our program launch for the micro-internship with both students and mentors on the right. And on the left, the tentative schedule that we suggested to the students and mentors. We had just an introduction meeting and 4 meetings discussing everything from problem formulation to literature review to developing an algorithm or experimenting. And finally, students presented some really amazing ideas. For example, one student explored vehicle routing to minimize pollution, which is similar to what Google Maps is now doing. So through all of these events, we've served over 50 students, many from historically underrepresented groups in computing and AI. We're hoping to reach additional historically underrepresented groups as we grow. In follow-up surveys after these events, all of the student respondents reported an increase in interest in AI. And we've also begun to conduct interviews about a year after the first micro-internship ended to see how students are doing. And all 5 students interviewed so far have pursued further opportunities in AI, from courses and hackathons to research and internships. So I'm really excited to continue to improve these programs to try to create the most useful possible experience for students. So finally, to conclude with some key takeaways and hopefully set up a little bit of time for discussion. So I believe that it is really important to take a holistic view of the AI for social impact pipeline, from gathering and analyzing data to multi-agent reasoning to deployment. I think this holistic view allows us to identify areas with uncertainty and plan to account for that in other portions of the pipeline. This requires us to use multiple methodologies throughout, and I went through a few examples like machine learning, domain adaptation, game theory, reinforcement learning, and multi-armed bandits, to name a few. I think the holistic view also allows us to acknowledge the role of humans in these systems, which requires us to not only reason about human behavior, including through human subject experiments, but also to be more inclusive as we design and deploy these systems. So to wrap up and hopefully start a discussion, I wanted to share this quote from the Director General of UNESCO, an agency of the United Nations supporting education, sciences, and culture. The 2 main points that I think she's making are that first, AI has a great deal of potential for positive impact in the world. And second, that we must work together with people from many fields and backgrounds, including domain experts, students, and those impacted by AI systems. And based on the experiences I shared with you today, I think these are great ways to ensure that AI is truly an opportunity for humanity. So with that, thank you so much. I'd love to take any questions. Thank you for your time today. And please, I would also love to hear more about what all of you are working on. Thank you so much.
Thank you so much. Thank you so much, Elizabeth. I think that was great. I mean, very inspiring. And I thought, I love seeing how different AI approaches are translated to real world problems. Like, it seems so obvious afterwards, but using the Stackelberg security game for poaching and multi-armed bandit to remove traps and satellite data to detect micronutrient, which is way out of the box. I love that. I think it's very cool and clever and inspiring. And definitely the work on Try AI is a great way to show a different sort of impact that can be done. So thank you for that. I'll just ask, are there any questions at this point? Megan, you could just, I think, ask, but I think I saw Megan put a question in the chat. For deployment of drone monitoring, have the groups you've worked with set certain governance roles or rules with changed practices? Does this have an impact in itself? For example, remove someone from the field, or
What was it? What was the example? Let me make sure I don't repeat it. Sorry.
Remove someone from the field, or is there potential for greater opportunities from the technologies being deployed? Also, are there space-time aspects for poaching risk, time of year, and etc.?
Great question. So yes, there have been some impacts of government regulations on some of these deployments. So for example, when we were working with Air Shepherd, they were thinking about trying to expand into another country, but I think that country sort of changed their drone regulations at one point, which made it more difficult for Air Shepherd to fly there. Air Shepherd operated by flying their drones potentially out of line of sight for many kilometers and for 2 hours long, so that they could have a little bit cover more area. But that's something that may not be allowed in all areas. The type of drone they used may not be allowed in all areas. So that definitely came up. And I'm sure that there are even more developments as we continue to see more and more of this technology. So it's a really important thing to consider. And we tried to just stay in touch with Air Shepherd as much as possible and support them in working on these deployments where possible. And then in terms of space-time aspects of poaching, we definitely did see some of that as well, especially in the project on poaching activity with multi-armed bandits. So in the little data that we did have, we did see some trends, like, for example, certain seasons were easier for poachers to get into the park. And so maybe we saw a little bit more poaching activity then. Whereas other seasons, it was really difficult to get into the park. So maybe there was less poaching activity. So that was definitely something that we saw. And some of my colleagues in Professor Tomby's group have looked a lot at trying to predict future poaching activity and sometimes have to include those kinds of factors for sure. Hopefully that answers your questions. Yes, thank you. Great questions.
Any other questions? Well, I have a few. So just we don't have a lot of time, but I'll just ask a little bit. So
please. Did
you have any ideas of the upcoming challenges, like prior to starting and definitely prior to deploying, like the human monitoring and limited resources and bounded rationality? So I'm assuming since the deployment takes time, so how did you kind of know to address these challenges ahead of time, or was it an ongoing kind of trade-off? It's always it's kind of a trick when you're actually deploying something.
Definitely. Yeah, so that particular part of the work, we didn't end up deploying the game theory related aspect. That was something we were still trying to understand the situation on the ground, and we ended up not being able to because we wanted to make sure everything was all good. But you know, the past few years have been a little bit difficult to try to do that for. But we did deploy the part about automatically detecting humans and animals in the videos. We deployed that for a few months. And that part for sure, as you mentioned, was lots of new challenges coming up quite a bit. I would say not all of it were things that we anticipated ahead of time. A lot of it ended up being going back and forth and just talking with our collaborators at Air Shepherd to try to understand what was going wrong, whether we needed to prioritize false positives or false negatives, for example. That was something where they wanted to actually prioritize minimizing false positives, which was surprising to me. But in some of the previous work that they had done, they found that if they had too many false positives coming up, then people would just ignore the tool altogether and kind of zone out potentially. So that was something we had to find out by iterating with them and testing it. So I think it's really important to have those close collaborations. And I think that lots of interesting research comes from that. So honestly, that work kind of inspired this work now that I mentioned on selective prediction, and some of the work that I'm doing now as well, in terms of how best to set up these human AI teams and interactions.
Thank you. It's really interesting. So we do have to go in a second. I just have one more question. So I feel, well, so you're working with real world domains, right? And you've been working with poaching and images. So are these systems still deployed? How does it work in terms of maintenance? And you know, you've now finished your postdoc, so you're a PhD and you're moved on. How does that work in terms of the maintenance of these like systems?
Right. Great question. Great question. So this particular work that I mentioned being deployed with Air Shepherd, we ended up having that deployed for a little bit of time, like about a month or two in the field. And then we ended up not deploying that anymore because Air Shepherd switched directions a little bit. The pandemic hit, so things kind of didn't work out again after that. So that is not deployed currently. So we haven't been maintaining that. So the main area to continue that work is either to find new collaborators who are interested, or to use some of the data that we collected to try to refine tools for potential other purposes as well. Like for example, we looked at potentially trying to detect wildfires or other methods of like looking for animals, for example. But all of that is just some potential directions to go in. And then in terms of the micronutrient deficiency, that work, we are still working with partners in Madagascar and at Harvard School of Public Health. And for that, there are some new team members joining now that I've graduated to try to continue the work, and I'm still working with them. So we're hoping to get to a system where we can deploy that with real policymakers, and hopefully try to help them make their resource allocation decisions based on that.
Fantastic. Thank you again, Elizabeth. I'm sorry you went a little bit over time.
No worries.
This was a fantastic talk, very inspiring. Appreciate your time and, great work. We hope to talk further in the future.
Definitely. Thanks.
I have a couple of questions too, if you can stick around, Elizabeth. That's okay. I don't know if you have to go more or you can hang around too.
No. I'm hoping to listen.
Okay, cool. First off, Elizabeth, thank you so much. I really liked all of this work, especially the mix of really practical application of AI. So not just the theoretical aspects, which are obviously great contributions, but applying it is awesome. I was really intrigued by this deferred only message stuff having better performance. And like, I think I spent a fair amount of the second half of your talk trying to work out why that could be possible and not really having a good idea. But one of the things I wondered is just whether there's something in sort of psychology or human nature that when you defer to someone and say that you're like requiring their opinion, let's say, whether they then put more effort into giving an answer because of it. So I wonder if there's something there, or whether you thought more about kind of other reasons for this.
Yeah, great question. So I would say that we focused a little bit more on trying to understand why predict only, or showing the prediction in general, was harming performance. So that was where we kind of directed our efforts there. But like you, we were kind of hypothesizing that the reason that defer only performed better is exactly as you said, trying to like maybe being a cue to people to concentrate a little bit harder, or maybe potentially spend a little bit more time looking at a particular case because maybe they know that it's uncertain, there was some difficulty there, so they're kind of on alert without hopefully being misled by that prediction message. But that's something that we're hoping to look into a little bit more going forward as well. So for example, if we were able to time people going through this study, for example, we could then maybe be able to tell if that's truly happening, they're spending more time, or try to understand other things that might be happening.
Yeah, or even do it with eye tracking and look at where they're, that'd be really interesting. Yes,
that would be definitely exciting. So fingers crossed we can make that happen.
Yeah. I thought the simulation work to generate your thermal images was really interesting too, and not something I would have ever thought of doing. But I wondered how well that worked in that situation and how transferable the work was, because I guess I was looking at your image and wondering like, what other objects are typically lit up in these? Are they just other animals, and other animals you're not interested in the conservation of, as in like they're not priority for poachers or something like that? And how much, say, the behavior of animals in your model and like their positioning and things like that mattered at all? And whether that was a sort of aspect of that research at all?
Right. Yes, great question. So when we were building that simulation environment, we did try to base it off of some of the regions where Air Shepherd was flying. So we kind of looked around at, say, Google Maps, Google Earth, to try to understand like what the terrain looked like in some of those areas, especially since we were only working from thermal data and it was kind of hard to tell. So we basically in that model had different levels of, for example, vegetation density. We had all of the different kinds of animals that we had seen, and even a few others that we thought might be in the African savanna, in environments that they might be flying drones in. And yeah, in terms of how we did their movements, so we ended up having, we ended up having the motion on just kind of a spline. So for example, you would have like a little route pre-programmed for the animals to take, and they would repeatedly go around those. So then we collected data by having our drone in the simulated environment follow one of these objects of interest throughout, let's say, a period of an hour, for example. And so while you do that, you also capture the movement from all of the other objects that were in the scene. And it ended up improving our performance by using that model. But we were interested in thinking of other ways to build in more kind of animal density or specific animal movement patterns into the simulation. That's something that we started to do. We had a challenge problem that we created and tried to allocate animals according to a specific density and try to have people figure out what the density was of the animals in the environment. But that was something, I think we still have it online somewhere, but we didn't end up doing a lot of follow-up work to that. So in terms of how generalizable all of this is, I think that one of the main generalizable insights was just that doing this was really helpful to not have to do all of that labeling work, or at least to augment all of the labeling work that we did. And it ended up working a little bit better than in that time using like a GAN, for example, or a generative model to create those images, just because we had the thermal images and they were pretty difficult to simulate sort of on their own because they were such tiny objects of interest, and it was all just kind of bright or dark spots in the single channel. If we were to think about that today, maybe it would be a little different, but I think that it was really helpful, and we even were able to use that simulated environment for some educational outreach demos.
I can totally imagine.
Yeah. So that part of it was also really exciting.
Yeah, for sure. I mean, it's a great way to be able to demonstrate the problem to people.
Right.
Yeah, for sure.
Yeah.
One of the questions I had with the automatic detection work that you put into practice, I guess you're also potentially detecting ranges, although I assume their positions are well known, and probably you're flying, or the drones are being flown in areas where the ranges are not. Like, is that information that's captured and known about and taken into account?
Yeah, so not necessarily in our model directly, but basically the way that the process would work is that there would be some detection, which would lead to an alert, maybe through like a ding on the computer, or just like highlighting the frame. And then the human operators there would call it in. So they would be able to say, yes, in this area, we know that there's a ranger, so we don't need to call it in, or another decision at that point.
Yeah, right. Sorry. And then my final question I had was just about working with Air Shepherd in this case. mean, assume all the drone flying happens in South Africa, but do they have a presence in the US and you were working with people in person, or was this all remote work? How did it come about? Because
Wow.
it's impressive that you, even if it was only done for a few months and in practice, it's great that you did it.
Thank you so much. Yeah, that's an excellent question. So it came about first by them hearing about my group's work on trying to prevent poaching. And so they were also trying to do that, heard about this work, and reached out to my advisor directly. And so then I joined the PhD program with him just as this project was starting. So I was able to kind of take it and run with it, which was wonderful. But yes, so they were based in South Africa. So most of the collaboration was remote. We were able to meet in person in the US once or twice. And eventually one of the people from Air Shepherd moved to the US and was based here, but they were in Texas and I was in California at the time. So we still didn't get to see each other in person, but the time zones were a little bit easier. So yeah, it was really it was primarily, I would say, virtual. And we always hoped to go there, and we think it's really valuable to work with people in person and understand kind of the situation on the ground. So that's something that I really value and think would be important, but we were able to do that here, and thankfully we're able to still work very closely with them virtually.
Great.
Yeah.
Oh, well, thank you so much for talking to our group. That's amazing.
Thank you, and it's a great talk. And once the talk goes online, then I'll also send you a link just for your records. And thank you. We really, really appreciate it, and we enjoyed it a lot.
Thank you so much. Thanks again for having me and for the great discussion. I really appreciate all of your questions.
You're welcome. Sorry for keeping you a little late.
No
Enjoy
worries.
your evening.
Thank you
Always
so
a
much.
good sign. Okay.
Yes, enjoy your
Bye-bye.
Friday. Bye.
Thank you.
Thank you.
Thank you.
Bye.